Solving the problems of the missile escaping from the Earth's gravity. Escape speed is not our luck in the escape velocity. We noted in item that the freely falling body is at the height close to the surface of the Earth. That is, the distance of the body from the surface of Earth is very small in relation to the radius of the Earth r. On the other hand, in the event the distance of the body from the surface of Earth is very large in relation to the radius of the Earth. For example, we launched missiles or spacecraft. We then use Newton's second laws of motion along with the high general law of gravitation. To derive the required differential equation, we can use the solution of the differential equation to calculate the minimum speed, which is called the escape velocity. It is the minimum speed that rocket needs to be freed from the Earth's gravity and launched into outer space. Example, a missile was launched horizontally upward from the surface of the Earth. If we consider the positive direction to be upward and neglected the air resistance, then the differential equation corresponding to the movement after the ignition of the fuel is minus k m small m capital divided by x square equal m d square x divided by dt square, and also k is larger than 0. D square x divided by d square dt square equals minus k m over x square, where k is the constant of the proportionality. The x 40 is the distance of the missile from the center of the Earth. Where m is the mass of the Earth and m is the mass of the missile. To calculate the constant k, let us use the fact when x equal r. So we get k equal gr square divided by m, and k m small dot m capital letter divided by r square equal mg, and also d square x divided by dt square equal minus g r square divided by x square. Although the previous differential equation is not the first order, we can rewrite it using the chain rule for the hardship and substitute it into acceleration as follows. D square x divided by dt square equal dv divided by dt equal dv divided by x multiplied dx divided by dt equal v multiplied dv divided by dx, and v multiplied dv divided by dx equal minus g multiplied r square divided by x square. Solve it by separating variable. Integration for v dv equal minus g r square integration for x minus square dx, and half v square equal g multiplied r square divided by x plus c. This is the equation number 1. If we can assume the speed v equal v naught when the missile is launched and x equal r at that moment, c equal gr plus v naught square divided by 2. By substituting the constant c in equation 1, we obtain the relationship between the distance of the missile from the center of the Earth and its speed. V square equal 2g multiplied r square divided by x minus 2gr plus v naught. We neglected the air resistance and the effect of gravity of any bodies other than the Earth. which we consider to be a sphere with the radius r equal 6,375 kilograms. On the Earth's gravitational acceleration at its surface is g equal 9.8 meter per second square. In order for the body to escape from Earth's gravity, v must be non-extant at x equal infinity. That requires that v naught square equal 2gr, that give us v naught equal under the root 2gr. V naught equal under the root 2 multiplied 9.8 multiplied 6,375 equal 11.1838 kilometers per second. Example, a spacecraft with an initial mass m is launched vertically upward with an initial speed v naught. If the mass of the fuel in the tank m naught larger than m naught, this increases due to the composition at constant rate of beta over a period of time t1, and the speed of the gas resulting from the composition of the fuel is equal to u, assuming that gravity is a constant and neglected air resistance. Find the speed when the fuel has been completely burned. The solution is the mass of the vehicle at any moment is m40 equal m naught minus beta t, and also t is smaller than t1. When t equal t1, the mass of the vehicle becomes m1 equal m naught minus beta t1 equal m naught minus mass of a fuel. dv divided by dt multiplied m40 equal m40 multiplied g plus u multiplied dm over dt. dv divided by dt equal minus g plus u multiplied u beta divided by m naught minus beta t, and m naught minus beta bt multiplied dv divided by dt equals minus m naught minus beta t multiplied by g plus u beta. The first order can be solved by separating the variables, and we obtain the general solution. V equal minus mg minus u ln for m naught minus beta t plus c. V equal v naught at t equal 0, that give us c equal m naught plus u ln m naught. When t is smaller than t1, v equal v naught minus gt plus u ln for the m naught divided by m naught minus beta t, and thus the speed when the fuel is completely burned is v1 equal v naught minus g multiplied m over beta plus limit for the m naught divided by m naught minus m fuel. If this speed is greater than the escape speed at the height that the vehicles reached at the moment, then the vehicle will be able to leave the Earth's gravitational field. Otherwise, it will return again to the surface of the Earth, the ground, unless other additional factors interferes with the movement of the vehicle. It is clear for the solution of the differential equation that the speed of the vehicles increasing with the increase and the speed of the gas resulting from the composition. On chapter gravities, 58.5 kilometers per second. On Saturn gravity is 35.6 kilometers per second. On Uranus gravity 21.2 kilometers per second. On Neptune gravities is 23.6 kilometers second. Thank you.